Hi everyone, my name is Andras. I'm a postdoc at the ISC in the Canary Islands, and here I'm summarizing our recent results on the problem of trying to understand the origin of the so-called CMB cold spot anomaly, for which one of the hypotheses is that a supervoid in its foreground might reprocess the incoming CMB light, making it a little bit colder via the ISW effect, and this could at least contribute to the observed coldness of this region in the sky. We are using the year 3 dataset from the Dark Energy Survey. You can see on the right that this analysis was not possible until this moment because the year 1 and science verification dataset did not yet cover this interesting area of the sky. In particular, the analysis that I led last year was built on the so-called reconstructed dark matter mass map, using the Dark Energy Survey data, which was a really complex analysis, starting from the raw DS data, relying on galaxy catalogs, then measuring gravitational lensing statistics, and ending up really with this very large accurate map of the dark matter distribution, including the region of the cold spot. And this is why it was interesting, right? So as you can see in the inset here, this is the cold spot itself, and this is on the right-hand side, our main results on finding actually this Eridanus supervoid in its location. You can see the striking correspondence between the largest void in the dark matter distribution and the coldest spot. You can see also on the left that this doesn't really change if we change our methodology. Well, the interesting thing, of course, is can this supervoid, given its size and emptiness, really explain the cold spot, for which the answer in lambda CDM at least is no, but I'm happy to explore other models or other ideas with you. Thank you.
Hello, everyone. My name is Chad Briddon from the University of Nottingham. Today I'll be telling you about the software that we've developing called SELCIE and how it can be used to help solve screen scalar field models in complex systems. So the code works for a model known as the chameleon model. We have made a version that works for the symmetron model. However, this is not yet publicly available yet. We hope to generalize this further to other screen scalar field models in the future, but for the purposes of this presentation, I'll just be focusing on the chameleon. The chameleon is a scalar field that couples two matter. Due to its nonlinear potential, it possesses a screening mechanism whereby the mass is a function of the local matter energy density given here by rho. What this means in practice is that in regions of relatively high density, so say the Earth or solar system, the mass of the field is large, and so Fifth forces mediated by it are suppressed. This is how it's able to avoid observational constraints. Now, the problem arises that due to this nonlinear potential, the equation of motion is very difficult to solve analytically, especially for non-symmetric systems. That's where our code comes in. Using SELCIE, you can construct systems with very complicated density profiles, and with just a few lines of code, you can solve the equations of motion to get the chameleon profile for that system. Here, for example, I have a chameleon-shaped source inside of a vacuum chamber, and I'm able to get the chameleon field profile of the chameleon. Using this, we could then construct experiments by looking at what the Fifth forces produced in this system would be. To show how much general we can make a system, in the various subdomains of your system, you can also have density profiles that are described by independent functions. So for practical examples, we've used this software already to investigate NFW galaxy profiles and cosmic voids. Thank you for listening. The link to the relevant papers and the GitHub for the code are below. Thank you.
Hello, my name is Daniel, and today I'm going to present you Relensing. This work is based on our paper, so you can go and check it out for further details. Relensing works on a grid which evolves over time following a process of refinement, where at any stage of the reconstruction we assign a deflection potential on the grid, which we use to compute the different quantities that we need for any given angular position. For that, we use the generalized finite differences method, such that at the end we get a free-form reconstruction. In order to compute the deflection potential, we have two levels of iterations, the outer level, which is responsible for the refinement, and the inner level, which we use to compute the deflection potential. To do so, we define a penalty function. We minimize that penalty function with respect to the deflection potential on the grid, and then we get a system of linear equations in terms of the deflection potential. As an example, here we have the reconstruction of a simulated galaxy cluster, where we can see the resemblance between the true map and the reconstructed map, where we have been able to recover the morphological properties of the distribution. Here we have the relative difference between those maps, where we can see that the best performance is achieved within the region enclosed by the multiple images. We have also been able to retrieve the shape and size of the magnification map, where the quality of our reconstruction becomes more evident when we directly compare the critical curves, the true and the reconstructed one. Since we have the deflection potential, we can also compare the caustic curves, as we can see in the image. If you have any questions or comments, feel free to reach us. Thank you.
Everyone, I am Giorgio Lesci. I'm a PhD student at the University of Bologna, and with this talk I'm going to summarize the work I'm carrying out on galaxy cluster statistics in KIDS. Starting from KIDS DR3, the Amico cluster sample here was actually an excellent sample for doing cosmology, both in terms of effective area and redshift range. Here the main goal was to constrain S8, in particular here in the right panel in black I show the result from clustering and in pink from counts. As we can see, these results are very competitive and in agreement within 1 sigma with Planck, WMAP, and with other cluster counts and cosmic shear analysis. In KIDS 1000, we want to do the same, but better, of course. There are several improvements, first in terms of photo-Z quality, and of course in terms of effective area. In addition, the reliable redshift range available for weak lensing mass calibration is wider. And also the analysis is blind, and we will jointly analyze weak lensing, counts, and clustering. And for doing so, the first step is deriving the mass richness relation directly from the cluster profiles, in particular by modeling all of them, all the stacked profiles jointly. In this way, the mass calibration depends on cosmology, and we can propagate local properties of galaxy clusters into the cosmological posteriors. And we can also then propagate the mass concentration relation. In particular, here I show it as a function of mass and redshift on the right. The gray bands represent our model within the 68% of confidence, and the other lines represent results from simulations. This is interesting, and we still have to understand this strange behavior at low mass, for example. So thank you a lot for attending, and I hope we will talk soon.
Hello, everyone. I am Grasiele, and I will give you a brief summary of my research. In your screen, you're seeing a schema of gravitational lens in which the object acting as a lens is a early type galaxy. In this case, there are two ways in which we can measure the mass of this object. First, by considering the lens effect, but also by considering the kinematic of the stars in this galaxy. Both of these quantities are related to the post-Newtonian parameter, and this parameter can be used to test gravity. Once it's supposed to be 1 in general relativity, or different than 1 in some modified gravity theories. So in order to measure the galactic mass through the kinematic of the stars, we have to solve the Dion's equation. And this equation depends on this parameter beta that measure the anisotropy between the tangential component of the velocity dispersion of the stars in the galaxy and the radial component of this velocity dispersion. This parameter is frequently assumed to be constant, but this is a source of systematic uncertainty. Once a slight difference in the value of beta can lead to a huge difference in the posterior of gamma. So how are we addressing this problem? If we look into the literature in galaxy dynamics, we shall see that beta is supposed to be highly dependent. So in my research, I am considering more general models of beta in order to modeling the velocity dispersion so I can estimate the posterior of gamma more accurately.
Lyman-Alpha tomography is an exciting technique to map the 3D structure of the intergalactic medium at cosmic noon. It is done by observing the Lyman-Alpha forest in the spectra of many Lyman break galaxies and quasars on the background, and then interpolating the absorption signal in between the sidelines. This figure shows the reconstruction quality of this technique using mock observations. Lyman-Alpha forest traces larger-scale structures, including protoclusters and protogroups. As this figure shows, these structures are highly blended. Therefore, we developed a method based on the watershed algorithm to delineate these structures. First, we visually test our model's success in this delineation task. On this figure, the diamonds are protoclusters and protogroups which we target, and the contours are derived from placing a simple threshold on the measured signal's significance. And this illustrates the watersheds derived from our method. Comparing the counts of protoclusters and protogroups in watersheds, the dash curve here, and those in the simple contours, the solid curve here, tells us that the watersheds isolate individual structures much better. One can use this technique to provide accurate mass estimation for galaxy protoclusters and protogroups, or to study the environmental dependence of galaxy evolution. If you're interested to learn more, please take a look at our paper. Thank you.
Hi everyone, my name is Miguel Enriquez. I'm in my last semester of my PhD at Universidad Autónoma del Estado de Morelos in Mexico. I'm working with professors Juan Carlos Hidalgo and Octavio Valenzuela, and I'm going to talk about my PhD project, which is about including non-Gaussianity and relativistic corrections to the initial conditions of cosmological simulations. Our main idea is to modify the gravitational potential kernels in the initial condition package to LPTIC and use it as input in cosmological gravitational solvers such as LP-COLA, adding relativistic corrections and non-Gaussianity via FNL and GNL parameters, and measuring the impact on the matter distribution. Because we're including non-Gaussianity, we are going to need high-order statistics like the bispectrum. The modifications are based on relativistic contributions that at linear level are the same as the Newtonian equations of motion. This helps us to maintain a Newtonian evolution, and the difference lies in the constraint equation, which is used to propose the initial conditions. The density solution with this scheme are these ones. We found an impact of 5% in the power spectrum at large scales, where we include the counting term that is commonly used to fix the difference at small scales between simulations and perturbative solutions. In the bispectrum, we found a difference of 16% at large scales in a squeeze configuration that corresponds to local non-Gaussianity. We already published these results at JCAP if you would like to see more details. For future work, we have planned to use adaptive mesh packages to analyze possible impacts at small scales and explore different triangle configurations. Thank you very much. If you have any questions or you want to continue a conversation on this topic, feel free to contact me.
Hi everyone, I'm going to present the work which I did with my supervisor, Professor Patrick Dasgupta. I'm very thankful to the organizers for allowing me this flash talk. A binary system consisting of two inspirally black holes emits gravitational waves, and these waves are confirmed by the gravitational wave detectors. In this work, we analyzed the electromagnetic fields and electromagnetic power and gravitational wave amplitude and gravitational wave power of the dionic black holes in a binary system. A dionic black hole is a black hole having both electric as well as magnetic charges. Here are some results with charge to mass ratio. So this Q is electric charge of black hole second, and the magnetic charge of black hole second is 0. Similarly, for first black hole, the electric charge is 0, and the magnetic charge is given by the Dirac quantization condition. Especially for this case, where charge to mass ratio for second black hole, the electric charge to mass ratio for the second black hole is 10 to the power minus 3 root g, and g1 is given by this. So we have the frequency and the electromagnetic power, which correspond to the FRBs, which is fast radio burst. So here is the summary of our work. So we have calculated the analytic solution of dynamics of Dyon-Dyon interactions, and now we are working with the back reaction problem. Back reaction means what will be the effect of these radiations and the angular momentum loss due to the radiation on the binary system. Thank you.
Hi, I want to talk about cosmological distances and Hubble tangent in Einstein-Cartan theory. In this work, we study the Hubble tangent problem in the framework of torsion theories of gravity, particularly Poincare sphere of gravity, and is a special case to Einstein-Cartan theory. Gravitational interactions are characterized by curvature and torsion in these theories, and the presence of torsion affects the cosmological dynamics in many ways. So here, first, are our Friedman equations in Einstein-Cartan theory, in which phi is the torsion. We determine the angular diameter distance while existing torsion, and as you can see here, the parameters omega for a homogeneous and isotropic model with torsion can be introduced like this. We can see here from the plot that the distance will be greater for a given z, and n comes from here, from omega phi. By determining the Hubble parameter in GR and Einstein-Cartan theory in both matter and radiation-dominated universe, we can see that we have a bigger value for Hubble in Einstein-Cartan theory. Here we can see it. The purple line shows GR and the pink line shows Einstein-Cartan, but our work is not finished yet. The Hubble constant can be evaluated by using the time delay between different images of a lensing system. As we have seen, the angular diameter distances for an object at a given redshift is greater in the presence of torsion compared to GR. This means that the evaluated Hubble constant from a lensing system is going to be smaller in Einstein-Cartan theory compared to GR. So as we said, at first, torsion alters the formulas for angular diameter distances and as well as the time delay between various images of a lensing system. These changes may alter the measurements of H0 and provide a way to solve the Hubble tangent problem. Thank you for listening.